Alright, hell yeah. So we have linear algebra, and today we're going to tackle what seems to be a pretty tricky problem. Now I did this at the coffee shop, so hopefully we're just going to do it in one go. But it says evaluate the determinant of this matrix. And one way to evaluate a determinant is if you were able to use Gaussian elimination to get all of these to be zeros. Cool, that's a start. And then you could use, is it still called Gaussian elimination? You know, because then that's in row echelon form. To get it into reduced row echelon form, you would turn all those into zeros. And then once you have your diagonals, you would just multiply the diagonals. But that requires all the operations here to do that, and then all the operations there to do that. So we're going to use lower-upper factorization or decomposition, however they want to say it. And the cool thing about it is because the second I get this to be 0, this is starting to form the upper matrix. You know, I get this 0, these zeros, then I just move it right along. But every step that I do is a elementary row operation to get this to be 0. And we're going to talk about that because that's the fundamentals of what's happening. But when we do that elementary operation, I'm going to take the inverse of it and then start building my lower from what I did to that. So if I turn this into a 0, you know, by multiplying the top by negative, well, in this case, multiplying the top by negative 1/3, cool. Then on my lower, I'm going to add a third. So hell yeah. All right. So booyah, let us begin. So the elementary row operations that we're going to be using is to get this to be 0. So let's start real simple and say this is a 2 by 2 matrix, 3, 1, 1, 3. And so we have 3, 1, 1, 3. Now think of these row operations as hey, oh, I dropped my pen. As this is matrix A, and or X, you know what I mean? Because you have AX is equal to B or something. X, this A matrix is just a transformation of a vector, you know what I mean? But just, we can think of it as, you know, if I have matrix A, I want to transform matrix A, and we're going to transform it by multiplying it by an elementary row operation. And so all this is just a matrix that's being transformed by another matrix. And the transformation process happens by multiplying 4 numbers, you know what I mean, or this matrix times that matrix. The elementary row operation to get this, so, you know what I mean, if I just have this 2 by 2 from just a Gaussian elimination, and you know what I mean, this is saying 3x plus 1y is equal to, you know what I mean, we don't have a solution vector, so we just kind of have this side of the equation. Hopefully I'm getting that right. And then plus 3y is equal to, you know what I mean. So all we're doing is saying that this, if I wanted to get this to be 0, well, I could put my division sign here, or I can either add or subtract these. But then I can multiply this whole thing. So let's say there was a and B over here. I can multiply this whole top equation by a third and negative a third, because I like to add. You know what I mean? I'm going to add the top to the bottom. So now when I multiply this negative a third all the way through, this becomes negative x. So we would have negative x. This would become negative 1/3 y, and if I had something over here, it would be negative a divided by 3. And then when I subtract these, I would have negative 1x plus, or I'm sorry, I'm going to add them. That's the whole, you know what I mean, I didn't want to lose my brain. So anyway, so we have negative 1 plus 1, so now we have 0x. So that's how we get that to be 0. And from just a Gaussian elimination perspective, I'm just going to multiply something. I'm going to multiply this row by a negative 3, and then I'm going to take this row and add it to this row. And so I'm modifying row 2 by multiplying row 1 by a multiplier, and then adding it to row 2. So row 2 is going to get modified. Row 1 will stay the same. And so when I multiply this through and then add it to row 2, this now becomes 0. This now is negative 1/3 minus a 9/3. So this is, I want to add. So negative 1/3 plus 9/3. So this value would become 8/3. And so we'll get to that in a second. Alright, but if we just have a 2 by 2, just to kind of keep it simple, how do I get this to be 0? Well, I'm going to multiply the top by a negative 1/3. And so this becomes a negative 1, and this becomes a negative 1/3. And then I'm going to add it to the bottom. So the bottom becomes 0, and then this is going to be 9/3. 3 is 9/3. So negative 1/3 minus, added to this row. Sorry, I keep saying minus. But negative 1/3 added to the second row is going to be 8/3. So this value becomes 8/3. Cool. So we just know how to do that, but what we're doing is a transformation. We changed this matrix. And so there was an elementary, and we just kind of did one thing to it. Even though we changed both values in this row, we still, that is an elementary row operation. And so the elementary row operation that we did, and let me go over both of those. I think that will be a good thing to do. So I'm going to start with the identity matrix. And I want to change the identity matrix. The two elementary row operations that we're going to be using, even though there's 3 of them. Whoa. Bummer. So to let's do the kind of the first one in the book. The first one in the book would be like, hey, just multiply this row by a value. And so I'm going to put this star right there. Sorry, bummer. Let's start over. So this is the elementary row operation to multiply this row by a scalar. You know what I mean? This only goes there. If I wanted to multiply the bottom, so we can kind of do, both of these are just multiplying a row. This one multiplies the top row. This one multiplies the bottom row. So let's do this. When we do scalar matrix multiplication, I have these two multiplied and added to these two. So that's going to be this up top. 0, 0, 0 right there. 0, 0, 0 right there, 0, 1. So sweet. So we can see that this was the identity matrix, and we should see that it's obvious that if we have this times the identity matrix, then we just have this. But what did this do? Well, it multiplied. If we said this was 1 and 0, what we did was multiply the entire top row by this scalar. So this could be 2, this could be whatever number you want it to be. Okay, and so that's elementary row. That's one of the elementary row operations. The other one is the one that we're going to try to do to get a 0 there. So I'm going to have and let's set this up like we have this. So we have 3, 3, 1, 1. And what I want to do is get this value to be 0. So I always start with the identity matrix, and then where am I going to put my value? I started with the identity matrix here, and I put my scalar right there on one of the diagonals. So I'm going to put my scalar on one of these. That's the two options. And if you forget, try one. You know what I mean? So I'm going to put my scalar multiple right there. And so it's going to be 1, 0. And what do you think I'm going to multiply the top row by? Well, we thought it was going to be negative 1/3, so let's just try that. Hell yeah. And hopefully this works. So we have 3, 3, and then 0. So and then this value right here is going to be 1 times 1 plus 0 times 3 is 1. We have negative 1/3 times 3 is going to be negative 1. Sorry, I haven't done the whole thing. So this value right here, this is in row 2, and it's in column 1. So I'm going to multiply row 2 by column 1. So we have negative 1/3 times 3 is negative 1, added to 1. So we get 0. Hell yeah, and that's what we wanted. this value, second row, second column, second row, second column. So this one's going to be negative 1/3 plus 3. So that's going to be negative 1/3 plus 9/3. And that's where we get 8/3 here. Hell yeah. And so we're just going to have to do that a bunch. But that's essentially what's going on. So that's the elementary row operation. That's the other elementary row operation. So there's two that we're going to be using throughout this problem. This one we're going to be using a ton. Okay, so now the proof. The proof says if this is matrix A, and we're just going to say matrix A is this 2 by 2, 3, 1, 1, 3. And essentially what I want to do is get matrix A to be a lower and an upper. So when I take matrix A and then multiply it by my first matrix or elementary row operation, I'm on the road to making an upper. So like this E times A, hey, maybe it's, I'm just going to say upper star. It might not be an upper yet, but at some point it will be an upper matrix. That's the whole point of taking A, doing these elementary row operations, get that to be 0, that to be 0. And I don't know, I think the proof on this one's pretty cool, probably just because I can do it. But let's say this was the first elementary row operation, and we had to do, and we can do 2 for this one. So the first elementary row operation got this, this value should have been 0, right? Yeah, so yeah, we got that. So this was A, so this now is that first elementary row operation times A. But now let's say I'm not satisfied enough, I want to get this to be a 1. So that's going to be multiplying that top matrix by 1/3. Or, I just want to multiply this whole top row by 1/3, and then I get 1 there, right? So that's going to be another elementary matrix operation. And so I always start with the identity so I don't lose my mind. And then put this right here. So this is 3, 0, 8/3. And just to keep up, this is matrix A, or elementary row operation number 1 that we did, times matrix A. So that is that matrix. And now we're going to do another elementary row operation. And so we just need to know which one. I can put the scalar value anywhere. Or I mean, if it's an elementary row operation, you're only going to be you're only going to put one number in one of these 4 quadrants. And if I'm going to modify this row, I'm going to put it on the diagonal, and it's going to be negative 1/3. So hell yeah. So that's E2. E1 right here, this was E1. Hell yeah. And this is cool because in the second, well, we're building the upper, by taking elementary row operation 2, 1, E, and then for sure we're going to get our upper then. And then we're going to use this proof to say we could have been building our lower at the same time. Our lower is going to be, and just to, to say what it is, it's going to be the identity matrix times E1, the inverse of E1 times the inverse of E2. And you can see how this goes in E2, E1A. This starts on this side, identity matrix E1 inverse, E2 inverse. And so we can see that this order 2, 1 is switched 1, 2. You know what I mean? While we always do matrix multiplication that way. You can group these. You can do that first if you wanted to, as long as you do it in that order, and then do this. It's associative, but it's just not commutative. Can't go the other direction. All right, hell yeah. And so this is perfect. This is what people aren't going to do on matrix videos from an elementary perspective. Is like, hey, let's start with the proof and then do the problem. People are just going to, and then it just feels like a lot of hand waving. And when they're doing the hand waving, they might mention the proof, but that's not good enough. You know what I mean? You really want to see what's happening. And so we're just doing this extra step. We have our upper, but we're just going to do this extra step to get that to be a 1, just because we want it to be a 1. So hell yeah, let's do our matrix multiplication. I want to know that value, first row, first column, first row, first column. So this multiplied is going to be, my bad. if this was our matrix and we wanted, yeah, it's not a negative. This gets me tripped up. It's because when we change a row, you know, there might be a negative sign involved. But when you're just trying to get this to be a value of 1, 3 divided by 3, or 3 or 1/3 multiplied by 3 is 1. So this is a positive 1/3, my bad. And then so first row, first column, these two multiplied are going to be 1 and plus 0. So we have a 1 there, and that's what we wanted. Second row, my bad. This is the first row, second column. First row, second column. We have 1/3 plus 0. Hell yeah. And then second row, first column. 0, 0. Hell yeah. And then 0, 8/3. Okay, and we can see all that did was just make this a third and this a third. You know, it didn't mess with the other. Hell yeah, but now we have, now this is A, elementary row operation 1, and then elementary row operation 2. We did them in this associative order, but we always did it this direction. You know what I mean? So matrix multiplication goes that way, but it is associative. Had I known that I could have just did both of those, I could have just done E2 times E1 and then do it to transform A. So that shows that it's associative. Hell yeah. Okay, so now for the proof. So now we for sure have this, E2, E1, A is equal to U. And I don't know, I always maybe get stumped up on like how to set up the proof, but we'll do it. Because I always write down like, what's our objective? Our objective is to get A as some lower times upper. And we know that if we build an upper, there has to be a matrix multiplied by that upper to get A. You know what I mean? And for all of these, matrix A is linearly independent. That is an important. It's invertible. It's a square matrix. It's, you know, if you reduced it to row echelon form, you would just have the identity matrix. You know, it would be reduced to 1. Is that true? All right, that's cool. I stumped myself, but I always, you know, I don't care about getting stumped. If you reduce this to row echelon form, you know, we haven't said this was multiplied by, you know, it's kind of in the form AX is equal to B. That's what I always thought. And then, but if I get this all to be zeros and we're left with a 3 down there, well, I can just divide both sides by 3. I can get this to be a 1. And then when I do my row echelon, and if I get all those to be zeros, technically I can just get 1s all the way across, and that just shows linear independence. So getting the bottom and the top to be all, you know, zeros, it's no longer matrix A though. That's the thing. Where, yeah, I'll have to. That's tripping me up, right now. But we'll stick with what we know. We know that we can take matrix A, we built an upper, and, oh, I think that's where this proof comes in. Cool, you built an upper. The upper isn't equal to A. Ah, that makes sense. If I take this elementary row operation and do that to A, this is no longer A. It's something else. You know what I mean? E1 times A, an elementary row operation times A. Now you have B. You know what I mean? And A is not equal to B. So I'm glad I'm doing this on the fly, because those things kind of trip you up. But we are going to say, hey, cool, I built this upper, and it's going to be very useful because it just has all zeros on the lower portion of it. But I'm going to say that there is a matrix that if we, you know what I mean, I'm going to say there is a matrix called the lower, or L, that when I multiply it by the upper that I got, it's going to return this original matrix. And so this is the actual proof, because we know what U is. You know what I mean? Check this out. U is right there. So I can sub these 3 values in for right there. Hell yeah. And but I forget, you know what I mean? So you could do that, but I kind of forget how this this proof rolls. Yeah, let's try that. You know what I mean? A is going to be the lower, and then we have E2, E1, A. So now we have that. Yeah, that's probably not how they do it. That's probably the tricky part about this proof. I'm sure you could probably get there. But hell yeah, we have A is the lower times the upper. Oh yeah, here we go. On this side, I'm going to put this in. No, let's see. Oh yeah, no duh. So this is, yeah, so here it is. So yeah, and I don't even know, you know what I mean? But if I want to get A back by itself, I'm going to do E2, E1, bracket this in, and take the inverse of it. And now I'm going to do that to both sides. So over here, E2, E1, bracket it in. And so now I took the inverse of this, you know what I mean? Because this, associative, I can put brackets around that. That's just a matrix. It's a 2 by 2 matrix. And so when I take the inverse times that, this becomes the identity matrix. And then when I do this side, if I take the inverse of this times u, you know what I mean? I don't know what that is, but what I do know is that the identity matrix times A is just A. So now I'm going to have A is equal to E2, E1 inverse times u. And then if I'm saying I want A as a lower and an upper, and at this point in the proof, you know what I mean, maybe this is just A is equal to BU. I got my upper. Who knows if this is actually a lower diagonal matrix? It just happens to be a lower diagonal matrix, but for all intents and purposes, it's just a matrix. So, but we want to know what that is. You know, I want to know what matrix multiplied by this upper returns A. And so here's the equation. But now we have to use a proposition, because this you could get into trouble and just be like, well, maybe this just factors through. But it's not this. It's not E2 inverse, E1 inverse. That is not what this is. And so, I mean, from here is just I just guess, because I say, well, let's say this is E1 inverse, E2 inverse U. You know what I mean? So that's what we're trying for, and we're trying to show that this lower is E1 inverse, E2 inverse. But we need a proof to do that. So that's going to be the next part of it. How do we prove that? Well, what we're going to say is that if I'm just going to guess this, if I'm going to say, well, now I have to see. Yeah, you know what I mean? That's the thing about proofs, is they're very like, hey, this is obviously what you do next. But when you're trying to do it from memory, I think it's good to do it from memory, because you're just like, well, we gotta follow some logic, and at some point we gotta see that. So I'm gonna take a little pause. All right, hell yeah. And I think it's the fact that you just use the identity. So, you know what I mean? This is the inverse. So I'm going to say, you know, E2, E1, bracket that in, multiplied by E2, E1 inverse. What does this have to give me? This has to give me the identity matrix. Cool. And so I can put this over here. Now I'm going to guess what this is. So I'm going to say E2, E1, and I'm going to guess correctly on this one. I'm going to say this is, I'm going to switch the orders, but I'm going to say this is E1 inverse, E2 inverse, and we're hoping this equals the identity. And now we can, you know, like right now the light bulb went on for me, but if this is your first rodeo, it's like, because matrix multiplication is associative, I can do those first. And we have a matrix times an inverse of that matrix. This is the identity. And then the proof can go very fast, because we have a matrix times the identity is just this matrix. And you could have done it this way. I could have then done this over here and been like, this identity times this is just that. So this goes away, and now I can put my next brackets between these two. And this is a matrix times the inverse of that matrix. This is the identity, and we have the identity is equal to the identity. Hell yeah. And so why is this useful? It's because when I start to modify A, so I'm going to modify A, and I'm going to have this E1, and then this is going to, well, let's do the kind of the whole proof. So we have E2, E1A is going to be, since we said it's such, is that this is now, so this is going to give us U. So this is going to give us U. But we want to say A is going to be the lower times the upper. And so we're going to say A is, now we know what the lower is. So that's where I should have slowed down. The lower now is this. That is a check on reality that for sure is the lower. So we have E1 inverse, E2 inverse. That's our lower. And now we're going to multiply it by the upper. And the upper is this. So it's E2, E1A. And so this is the upper. So we have lower times upper. Cool. And what we can say is that the lower, all the values are going to be added on right there. So if we did a third elementary row operation, we'd have to squeeze that in right there. And then we would have the elementary row operation number 3 on, that matrix. We can always do another one. And this is why they say build your lower, because if this is the lower, we're going to build it from an identity matrix. I can put an identity matrix anywhere, but I'm going to put it right there because, hey, look at this. This is the first thing we did over here to matrix A. And so I can start the process of saying, hey, let's take the identity and multiply it. And yeah, I guess, oh man, I'm going to run into, no, this is good. This is good. I mean, you can put the identity here, but I'm going to show you one thing that's going to get you into trouble. Yes, you can multiply this. I can have the identity, I can do E1 inverse. But what we should think of is taking this identity and putting it right there. You know what I mean? So I have E1, the inverse of that first elementary row operation, times the identity matrix. Hell yeah. Then once you get that, which is just the E1 inverse, then when you do the second elementary row operation, you're going to be able to do this E2 inverse. But you're going to have this matrix, and then you're going to put the E2 inverse right there. So that's very important, is that this... You know what I mean? Because like when you're building it, and no one builds it like that, they just use the hand waving. But this is what's going on. If you did it in the reverse order, you'd be doing it wrong. And yes, elementary row operations are not commutative. I think maybe 1 or 2 are. Like, if you're just multiplying, if you're multiplying the rows together, I think that's commutative. But if you are... Yes. If you're just multiplying the rows together, that's commutative. Yeah, so that's going to be for another video. But there's 3 different types of elementary row operations. And I think if you're switching from one to another, that's how it works. Like, if you're only doing, if you're only doing this, like, changing, multiplying that first row and then adding it to the second row. If you're only doing operations like that, I think it is commutative, but don't quote me on that. So hell yeah, it's just interesting to see the order that you need to multiply those. But when people build their lower, they just do a lot of hand waving. Okay, and we're just going to do the hand waving as well, you know what I mean, because we know this as a proof, and maybe we can do a little bit more than hand waving. Let me throw another battery in, take a little break. And we're going to start this problem. Booyah. Alright, hell yeah. Okay, we're back. And so, let's do this. So how I start these, especially because they can get out of control pretty fast, is I'm going to kind of rewrite this matrix. And I'm going to do 5 dots. That's 3, 4, 5. And I'm going to do 5 rows. So that's the second row. That's the 4th row. Okay, hell yeah. And then I can rewrite that in if I want to. I'm going to be building my lower, so I'm going to put 3, 4, 5. 1, 2, 3, 4, 5. I'm going to do this 5 rows. That's the 3rd row. That's the 5th row. If this is my lower, I'm going to multiply it by the upper, and then I can do a double check on reality that I have the original matrix. So I'm going to do another 5. First row, second row, fourth row. Hell yeah. Okay, so this is going to be the upper. And the first thing that, you know what I mean? Like, we can do any elementary row operations we want. I could change this first row. I could change this. Remember, this is matrix A, and the first thing we're going to do is our first elementary row operation. So I could do a multiply this first row by a third, and that would be a 1 right there. I don't need to, because all I'm trying to do is get a upper matrix while building the lower. And the whole idea of the determinant of an upper matrix is just the multiplication of the diagonals. The determinant of the lower is the multiplication of those diagonals. If the determinant of A is going to be the determinant of the lower multiplied by the determinant of the upper. You know what I mean? So that's why this is so easy, maybe. And again, I forget, if you do Gaussian elimination to get an upper, can you take this? I think if you just go into reduced row echelon form, it all just becomes 1, because it just shows that it's linearly independent, especially if you're not comparing it to any set of solution out here. Is that the case? I forget. You know what I mean? So that's the only wishy-washy thing I'm not good on. All right, but first thing we're gonna do, we're gonna get that to be a 0. How do we do that? We're gonna do an elementary row operation where that which is, I want to change row 2 by multiplying row 1 by something and then adding it to row 2. So if both these are positive, I need to multiply row 2 by a negative something, and if then I'm going to be adding, negative 1 plus 1 would be 0. So a negative multiple, so it's going to be a negative 1/3. Cool. What's the elementary row operation? It's kind of difficult to show. We showed a 2 by 2, but if it's a 5 by 5, now that elementary row operation would go like right here, but let's show it. You know what I mean? At least show the first one. And so, and let's show it right here. You know what I mean? So if we're going to do E1, what the hell would that even look like? Well, we said that the 2 elementary row operations that we could do are, one, we could put the thing on the diagonal, you know what I mean, the multiplier on the diagonal. The other, we could put the multiplier where the 0 is. If we put the multiplier where the 0 is, this effectively says I want to change this row by multiplying this first row by, and then, you know what I mean, by this multiplier, and then add it to this row. And it's fascinating that that does all that. But think about it. If I have this, an identity matrix, and I want to get this value to be 2, I cannot just multiply this row by 2. So what am I going to do? Well, I'm going to have to multiply this row by 2. Cool. And then I'm going to have to add it to this row. So that's essentially, if I want to get this to be 2, I got to multiply this row by 2 and then add it to there. If I wanted this row to be negative 2, I got to multiply this row by negative 2. So that's more similar to what we have. I have a positive 1 here. I have to multiply the top row by that negative value. So that really kind of shows that. So what would this look like? And then it doesn't matter if it's 2 by 2, you know what I mean? I'm doing this. This thing is saying I want to, like where this thing is so for this elementary row operation, it says that I want to change this row by multiplying another row by this scalar. But because of this value is right there, and if it's in a bigger identity matrix, and this is the value that I'm putting on there, if I multiply this by 2 right there, or if that's a 2 right there, I can't, and then I use that 2 to multiply this row 3. Cool, this row 3 becomes that, and then if I added it to row 2, then that value would change. You know what I mean? So because I'm putting the multiplier right there, it can only multiply row 1 and then add to row 2. So hell yeah. So even like right here, I want to say, hey, I want to change row 2, and I want to change this value in row 2 by a multiple of row 3. And just because we're doing upper and lower, I could choose this value if I wanted to say, hey, I want to change that value to anything, and I'm just choosing to change it to 0. Hell yeah. And if it's this value that I want to change, I want to change this value by multiplying it by the. Now, would that work? Yeah. Because it would be, I want to change this value by multiplying the top row. But when I multiply the top row, only this one's in charge of changing that value. You know what I mean? The others will change to different numbers. But if I want to change this value to a 0, you know what I mean? Because I'm putting the star right there, you know what I mean? Because this would be a 1, 1, 1, 1, 1, and then we would have 0, 0, 0, 0, and then 0, and then the star would be right there on that value, and then 0, 0, 0. So this says it's multiplying the top row by this. Oh, I feel like it doesn't make sense either. Damn it. All right, hell yeah. I'm just gonna say that probably wasn't true, but you know what I mean. But if we're just doing this in a standard way, what this elementary matrix is going to look like an identity. 1, 2, 3, 4, 5, and then these are going to be zeros, 4 zeros, 4 zeros. The multiplier is going to be, we want to change this value, so the multiplier is going to be right there. Oh yeah, and that's kind of interesting. And because this multiplier is right there, the row that it's affecting is that row. So if we came over to here, what the hell I was saying, you know what I mean, I want to change this value, well, by putting the multiplier right there, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 1, 2, 1, 2, 3, 4, 1, 2, 3, oof, damn it, 1, I don't have enough rows there. But yeah, if I wanted to change that value, this value is acting on that row. And so just by this elementary row operation, if it's going to change that value, it's multiplying this row. I mean, because this is an identity matrix with one value, with only one value kind of changed, then it will only modify. Yeah, what this says, like verbally, is say, hey, take this row and multiply it by that value, and then add it to this row. And I think that's correct, because that's what we're doing over here. It was good just to choose some random point to kind of see how that affects it. Okay, sweet. And so this value is going to be, that -3. So I'm going to put a -3 right there. And this is 1, 2, 1, 2, 3. This is the elementary row. This is E1. And so when we start to build our lower, well, we can already do that because we said it's going to be the identity times E1 inverse. And then once we get E2, we're going to put it on this side. But we can do this. So now our lower is going to be this. It looks like right now I'm going to make a mistake. It looks like I just put the -3 there. But no, this is E1. This says we're going to build our lower by taking the inverse of E1. Now the inverse of this matrix is just that value with a sign change. And that seems hand-wavy too. So the inverse of any matrix is 1 divided by the determinant of that matrix times the cofactor transformed. So we will do this one, because if you don't, then you're not going to have you're going to lose that fundamental understanding. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 1, 2, 1. Hell yeah. And then we got 1, 2, 3, 4. 1, 2, 3, 1, 2. And we got a -3 right here. What's the inverse of this? is going to be 1 divided by the determinant. The determinant is just the multiplication of the diagonals, if we want to kind of use that rule. Else, you know what I mean? I'm going to pick a row or a column, like pick this row, and take the cofactor transformed. Cool, cool, cool. And then I'm just left with 1. You know what I mean? And that's it. Everything else is going to be 0. So you can do it 2 different ways. So hell yeah. So this determinant's going to be 1. We got 1 divided by 1 is 1. So the cofactor transformed will basically give us the inverse. And so what's the cofactor? Well, if I want to find the cofactor of this location, it's the minor of that location with the sign change. This location doesn't transform, you know what I mean? Because this would go to there, but this diagonal stays put, and the cofactor of it is the minor at this location with the sign change. But these are positive values because it's I plus j to the negative 1. So if you want to follow that times the minor, and so this spot is 1 plus 1. This spot is row 2, column 1. But this is an odd spot, row 2, column 1. 2 plus 3 is negative, so that's where you get that sign change. So kind of just, being able to talk through that fast. But hell yeah, so this diagonal is going to be the minor of this, and then the minor of the remainder is going to be, the minor is the determinant of the remainder. The determinant of the remainder is pick a row or column, like this one, and then take this value times the cofactor. And then there is no sign change, and the cofactor is the minor without a sign change of the determinant of the remainder. The determinant of this new matrix is pick a row or column. I'm going to pick this one, and I'm going to take the cofactor of that location, no sign change, so it's the determinant of the remainder. Now I'm left with a 2 by 2, and the determinant's 1 times 1 minus 0 times 0. So the determinant of that's 1. And that was the process. Now I got to do it for this value right here. You know what I mean? Because the determinant of this entire matrix is this, number 1 times the cofactor of that location. So that's what we did. But now if I take this number 0 times the cofactor of that location, well, it's just going to be zeros across the board. So hell yeah. So the determinant of that is 1. So that's kind of the formal proof on that. Get some water. All right, hell yeah. So, wait, yeah. What the hell were we even doing? Oh, no. We just wanted to find... I mixed up 2 things there. I wanted to find the cofactor of this location, and then it's the determinant of the remainder. The determinant of the remainder is 1. So that position is 1. Now I'm going to go to this position. The cofactor of this location is the minor of that location, so I'm going to get rid of that row and column. And then the remainder matrix is going to reduce to 1. Nah. The remainder matrix, if I'm... No, yeah, because that's 1. If I'm finding the cofactor of that location, hell yeah. And then same thing for here. Get rid of that row, that column. You know what I mean? The remainder matrix, I'm going to use these 4 values. Get rid of that row or column. That gets rid of that negative 3. Hell yeah. Even this one, the cofactor of that location, I'm going to use maybe these values. And then so this is the only one that's going to dominate. And we're going to find the minor of that location. The determinant of the remainder is use this. Find the minor of that location. And then I'm left with this. Oh, yeah. So that's interesting. The cofactor. Oh, yeah. And then the determinant of this is just 1 times 1 minus negative 3 times 0. So that's just 1. Okay, sweet. So, but, when I take the inverse of this, I'm probably going to get something in this location. The inverse is 1 divided by the determinant times the cofactor transformed. So I'm going to take the cofactor at this location, and it should be a value. Maybe it's 3. Maybe it's negative 3. But that value will go into that spot. So when I'm building this, I already know 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. So here's my diagonal. I already know basically all those are zeros, and we're just trying to find maybe this spot, which is the cofactor of this location. So let's do that. This row and this, which is the minor at this location. The cofactor of this location is the minor at this location with a sign change. So the minor at this location, get rid of that row and column. Now I'm going to choose, I can choose anything I want to, but I could choose like these 4 values. So let's do that. I'm going to get rid of that row in this column, and then I'm going to take the determinant of the remainder. I'm going to choose those 3 values. I'm going to take the cofactor at that, which is on the diagonal, so it's the minor of that, so I can get rid of that row and column. Now I'm left with that 4 by 4, and I'm going to find the determinant, which is -3. So that's the determinant, and that's the minor. But the cofactor of this location is with a sign change. So that -3 becomes +3. And I think that's worth going through, especially on a 5 by 5. So you can kind of just say, well, yeah, everything else would have been 0. The cofactor of this location, you know what I mean? The cofactor of this location, with the inverse will be right there. But yeah, so I think we're done for the sake of time. We still need to get to our juicy problem. Alright, hell yeah. But this is E1 inverse, and like we said, our lower is going to be this identity. We're going to start with the identity matrix, and then start building upon it. Hell yeah. And this is where I think, does it matter? I don't know. I guess, I think it doesn't matter whether you take this and multiply it over there once you have this. Once you've done I don't know. I think there is an order. I think you got to do it in that order. Don't quote me on that. I mean, the proof shows that you have to take this matrix, and then if I multiplied it by E2, E2 would be on this side, or E2 inverse. So hell yeah. So, but yeah, this identity matrix times E1, you know what I mean, we're going to get a 3 there. And why? Because I'm going to, this is going to be first row, second row, first column, and I'm going to take this identity matrix and multiply this inverse. So, second row, and yeah, let's say this just was the identity. Second row, first column, so we would have 0 times 1 plus 3 times 0 plus 0, 0, 0. So this value is 3. Okay, cool. But yeah, that's a heady process. All right, so let's try to do this problem. All right, hell yeah. So I'm going to keep this upper row the same, 3, 1, and then 1's all the way across. I got a 0 here, so we might as well, so, you know, I'm using this, and that's where if you're doing 3 things, it's like, I don't have a 0 there. Well, no, this is the lower, but this upper, yeah, this upper is 3, 1, 1, 1, 1. So these are going to be the same. So I'm just showing you, like, while we're building it, and then we can put it here if we want to. Okay, so we're going to get a 0 here, because we multiplied the top row by a -3rd. So this value right here is going to be a -1/3 plus, this is 9/3. So that is tricky. The upper row is -1/3, because we multiplied that by that. And then we're adding 3, which is 9/3. So we have 8/3. So that can be difficult to see your first go around. This next one is -1/3 plus 3/3, because 1 is 3/3. -1 plus 3/3 is 2/3. Luckily, these are going to be the same. -1/3 plus 3/3, 2/3. And I'm going to get 2/3 right there. Okay, sweet. Now we're ready for our next elementary row operation. So all we did was change row 2, left row 1 the same. All of these would be just that. You know, I haven't done anything to them. So now I want to change this value. So we're going to use the process of, like, if this is our identity matrix, you know, I want to change that value right there. And so obviously this would be a 5 by 5. But here's going to be E2. And to change that value, I'm going to multiply this top row. What do I need to multiply the top row by? -1. Even if you need to multiply the top row by 1, you still need to show that process. if this was a negative 1 and then the top, or if this was a negative 3, you would multiply the top row by 1, but you would still do that elementary row operation. You still have to multiply the top row by something and then add it to this row to change it. You know what I mean? So there you got 2 steps going on, and yes, the multiplier can be 1. Okay, sweet. So we're going to multiply that top row by negative 1. And then so our E2, the next value of E2 is going to, like if this was E1, the next value of E2 is going to be negative 1 right there. And then so E2 inverse is going to be a value of 1 right there. So that's why they say you can start building your lower, because we're having this now. And then if you do this matrix multiplication, it's not going to affect anything except adding that value of 1, that positive 1. And so that's where it's just really easy to hand wave and be like, hey, well, this one, and it's really easy to hand wave if you change your top value to 1. If this is a 1, then whatever this value is just goes right there. Because we didn't change our top row to a 1 and then a 1/3, 1/3, 1/3, 1/3. I did that the first time actually around. So I'm actually doing it a little different, which makes it a little bit headier. Had I done this, if I changed my top row by this, then this 3 would pop up right there. But the elementary row operation to do that on this top row, this would have been a 1/3. You know what I mean? Because I multiplied everything through by a 1/3. No, this would be, the lower would be probably a 3 or something, and then this would be a 1. Yep. So the lower is a 1, this is a 3. Had I multiplied this upper by a 1/3, the inverse of that is 3 right there. Hell yeah. So actually, you probably should have done that, multiplied this top row by, get that value to be 1, but we're going to continue on. So yeah, so there's no easy double check right here, you know what I mean, because I multiplied by a negative 1, so this becomes positive 1. Why? Because this negative 1 is E2, and the inverse of that is a positive 1. So instead of just the hand wavy process of like building your lower, now you kind of know where that comes from. Okay, sweet. So we have 3 times negative 3. This negative 1 gets multiplied all the way through. Negative 3 plus 3 is 0. So we're going to get a 0 there. And then we got negative 1 plus 1 is 0. We have negative 1 plus 3 is 2. We have negative 1 plus 1 is 0. And then we have negative 1 plus 1 is 0. Hell yeah, so we're doing pretty good. Now this one, we want to know what to multiply. Now we have to do, we have to multiply the top by a negative 1/3. You know what I mean? So that, yeah. And then the lower, there's going to be a positive 1/3 here. But when we multiply the top, because if we multiply, the elementary row operation is to do this and have a negative 1/3 in that starred position. And if it's in this position, it affects that identity matrix, the 1, 1, 1's up there. So it changes row 1 and adds it to row 2. That's what that would be the third elementary row operation. And if that's the third one and it's a negative 1/3, then it's going to be a positive 1/3. Cool. Okay, so negative 1/3 is negative 1 plus 1 is 0. Negative 1/3 times 1 is negative 1/3 plus 9. So we have negative 1/3 plus 9/3 is 8/3. Negative 1/3 plus 3/3 is 2/3. So you can get off on those. You can definitely make mistakes. Negative 1/3 plus 9/3 is 8/3. Negative 1/3 plus 3/3 is 2/3. And this is cool. I'm doing this problem in a different way. You know what I mean? So that is very useful even for me. Okay, this next one. The multiplier up here is a negative 1. We have a positive 1. Why? Because the multiplier is a negative 1. E4 is going to be a negative 1 down here. You know what I mean? And then the inverse of E4 is going to be a positive 1. And we're building our lower, which is now we're up to like E4. Cool. Alright, so if I'm going to change this value, negative 1 times 3 is negative 3 plus 3 is 0. Negative 1 times 1. Negative 1 plus 1 is 0. Negative 1 plus 3 is 2. Negative 1 plus 1 is 0. Negative 1 plus 3 is 2. Hell yeah. Okay, so we're starting to build our upper. This is the only, now we have to deal with that. And this is, I mean, do we want to do an elementary row operation at least once to show, like, you know what I mean, to get this to be a 1? I mean, we don't have to, and we really shouldn't. Because even like right now, it's like the most evident thing we can do is if I multiply this row, because now we got our, like this matrix is now over here. Now this is the one we're looking at. I'm going to multiply the top row by a negative 1, and then these will cancel. So hell yeah. But this row, do I need to do anything? No. You could say it's an elementary row operation of taking that value, you know what I mean, and that value, you start with the identity matrix, and that value, well, that value is just going to be 0. So you can say I'm just going to multiply by the identity matrix to get that. The inverse of the identity matrix makes that 0. So you can think of it that way. Or just no change. Hell yeah, but all of these are 0 until something multiplies them otherwise. Alright, sweet. Because our elementary row operation is a negative 1, the inverse of that is a positive 1. So we're going to have a positive 1 right here. And we have negative 8/3 plus 8/3. My bad. No, we're good. But yeah, this is the lower. But here we got to modify this. So negative 8/3 plus 1/3. This is going to be 0. So now it's going to get a little tight. Negative 2/3 plus 2/3 is 0. Negative 2/3 plus 8/3 is 6/3. 6/3 is 2. Hell yeah. Negative 2/3 plus 2/3 is 0. Hell yeah. Okay, so we're doing pretty good. We have our, and at any point what I like to do is, like, if you have your final values, you can just do that. And at no point do you actually need to do the other elementary row operation of changing this value to 1. You know what I mean? If it visually helps you, but you don't have to ever do that. And even like right here, I can just see that I'm just going to apply another negative 1 to this. But let's go through. I didn't do anything here. And then I didn't do, what do we have? We have that value. Didn't do anything there. So this value, if I want to change it to a 0, I got to do an elementary row operation of negative 1. And so, and that's going to be a positive 1 right there. And so I'm going to have negative 2 plus 2 is 0. Negative 1 times 0 plus 0, that's 0. Negative 1 times 0 plus 2 is 2. So we did it. There is our upper. And this is a 0, these are zeros, and then we have those. But it doesn't matter because we're just trying to find the determinant. And this is our lower. Our lowers had all 1s because we didn't. The reason we have all 1s in here is because we didn't use that other elementary row operation of taking, you know, the identity matrix and then changing one of the rows. You know, that is an elementary row operation that will change that row of that matrix. And we didn't do that. That is the reason why we have all 1s here. If you chose to do some of these values, and at the coffee shop, I first just changed that to a 1. So on a speed run, I might do that. I might film myself and we'll just like crush it out. But hell yeah. And so now we're just ready to do the answer. Because if we have upper and lower, and here's our upper. So we have 0, 0. If this is an upper, these are all zeros, right? We have 2, 2, 2, and 8/3. We have 2/3, 2/3, and 2/3. 0, 0, 0. Hell yeah. And if we wanted to check this, you know what I mean? Let's, since I printed out plenty. Hell yeah. So this is, so this lower and upper should equal this. Let's at least check this first row. So 1 times 3 is 3, bunch of zeros. Hell yeah. Check just random middle diagonal. 1 times 1 is 1 plus 0 plus 2 is 3. Hell yeah. And the rest is zeros. Cool. So we're good there. How about this row? Check that value. Well, that's just 1. So which one? Like, ooh, look at that row. So we have 4th row, 4th column has to be 3. So we have 1/3 plus 2/3 is 1 plus 2 is 3. That's probably the most complicated row and column. So we look pretty good on that. Okay, so now I'm just going to feel, you could double check that 100%, and if you did, then you would know that now your determinant is just the determinant of L multiplied by the determinant of U. The determinant of L is the diagonals, which is just 1. This determinant is going to be 3 8/3 2 times 2 times 2. And you should be able to see that these 2's are an 8. So we have 8/3 times 8. Oh, yeah. I thought something was going to cancel. But no. These 3's cancel. Alright, hell yeah. So just the 3's cancel. So we have 8 times 8. The 3's cancel. 8 times 8. 8 times 8 is 64. And guess what? Hell yeah. Drop the pen. That's the answer for this problem. So hell yeah. If you want to do it on your own, you find a way to do it. I guess I only printed out a couple. Well, I printed out 3. So that was this page. And this was the original page. Hell yeah. And then we did the proof. So I'll put that right there. Hell yeah. Alright, thanks for joining me on this one. Booyah.